The angles in blue are examples of angles in standard position. The angles in purple are examples of angles that are not in standard position. So if you compare the two, what do you think constitutes an angle in standard position? Well, you might notice that we have a vertex on the origin, and one of those rays is on the positive x-axis. Vertex on the origin, positive x-axis, vertex on the origin, positive x-axis. Here, we do not have a vertex on the origin. Here, we do not have an arm on the positive x-axis, nor do we in this case. An angle in standard position, we're going to have the vertex of that angle at the origin. The ray that lies on the positive x-axis is what we call the initial arm, and in this course, we're going to rotate this other arm counterclockwise. That's going to give us a positive angle here, and where we end up, this ray is what we call the terminal arm of the angle. Initial arm, where we begin, we're going counterclockwise until we get to the terminal arm where we stop. So think terminate, stop, we end here. So start on the initial arm, rotate counterclockwise. Where we end up, this theta is our angle of rotation. A reference angle is the acute angle that's formed between the terminal arm and the x-axis, and it has to be the x-axis. So for example, on this one, this is not a reference angle because it's between the terminal arm and the y-axis. Same thing here. This is not the reference angle. This is between the y-axis and the terminal arm. So make sure your reference angle is between the x-axis and the terminal arm, and it has to be acute. So for example, it would not be this angle here. So in purple, we have the angle of rotation. In green, we have the reference angle. So in my first one, you can see that the angle of rotation is just that reference angle. If we terminate in quadrant 2, then my angle of rotation is from here to here. My reference angle is here. I can determine the measure of that angle because we know that from here to here is 180 degrees. So if we go 180 degrees, take off that angle of rotation, and it leaves us with the reference angle. If we terminate in quadrant 3, again, we know the angle of rotation. If we take off that 180 degrees, it will leave us with that reference angle. And in quadrant 4, we know that a full circle would be 360 degrees. So if I go 360 degrees, take off that angle of rotation, I'm left with my reference angle. We previewed the special right triangles in 10 AP as a way to determine the exact trigonometric ratios for angles of 30 degrees, 60 degrees, or 45 degrees. And at that point, we looked at how this triangle has a 1-to-1 side ratio, this triangle has a 1-to-2 side ratio, and then from there, we're able to generate those angle values. So today, we're going to kind of take a different approach. If we know we have a right triangle, this angle is 90 degrees, 45 degrees and 45 degrees. Base angles the same makes this an isosceles triangle. So I know that this side is equal to this side, and the easiest number to work with is just a 1-to-1 ratio, but this could be anything. So this could be a 2-to-2, this could be 5, and this could be 5, but these two sides are always going to have the same measure. And then we can determine the measure of this hypotenuse using Pythagoras' theorem. So I'm just going to say this is x for right now. That's our unknown side that we're looking for that length. So we can take 1 squared plus 1 squared equals c squared, or in this case x squared, and go ahead and calculate this. And then when you take the square root of that variable in order to isolate x, we only have the positive root because this is a length and we can't have a negative length. So we know that this hypotenuse is going to be the square root of 2. And remember that we can put any number in here for either of these sides. So if I know that I have 45 degree isosceles triangle, let's say that this has the length of 10 centimeters. We know this has a length of 10 centimeters. This is now 10 centimeters times the square root of 2. Or if this has a length of 20 centimeters, this has a length of 20 centimeters, this would be 20 times the square root of 2. So they work in relationship with one another. Our second special right triangle, so the 30, 60, 90 one, I'm just going to rotate that one and have it sitting up like that. And then I'm going to reflect that image onto itself to get this triangle, which I can now see as equilateral. So I have a 60, 60, and then this together would be 60-degree angle. So that tells me that this side, and then this entire side on the base have the same length. So again, 1 is the easiest number to work with. So if this is a measure of 1, this is a measure of 1, this is a measure of 1. But because I'm going to be taking only half of that base, let's say that this is 2, and then this base would have a length of 2. So now we can see that this side, opposite from the right angle, is going to have a measure of 2. We can see that this side across from that 30-degree angle is going to be half of that 2, which gives that a length of 1. And then because this is a right triangle, we can also use Pythagoras' theorem to determine this side. 2 squared minus 1 squared as an exact value is the square root of 3. Again, these sides are proportionate. So if this happens to have a length of 5 units, this now has a length of 10 units, double that. This has a length of 5 times the square root of 3. So when you're dealing with these special triangles, you want to remember if we have a 45-45 angle, it's isosceles, we have a 1-to-1 relationship. So those two sides are the same length. If we have a 30-60-90 triangle, the side lengths have a 1-to-2 relationship, short side to hypotenuse. And always remember the shortest side is opposite the smallest angle. And now we're able to generate those exact trig ratios. So if we're dealing with this one, so sine we know is opposite over hypotenuse. So you can start at either of those angles. So let's say we pick this one. So opposite over hypotenuse. And remember, we don't want to leave a radical in the denominator. So I'm going to rationalize, multiply by that radical in the denominator, divided by itself. And then we're going to get square root of 2 over 2. Cosine is the adjacent side over the hypotenuse. So again, we're going to have the square root of 2 over 2. Tangent, opposite over adjacent. And then over here, if we use 30 degrees as our angle, sine, opposite over hypotenuse, which is that 1/2. Cosine, adjacent over hypotenuse, so square root of 3 over 2. And tangent of 30 is going to be opposite over adjacent. And again, we don't want to leave a radical in the denominator, so we're going to go ahead and rationalize that. 60 degrees, we have opposite, square root of 3 over 2. Adjacent, we have 1 over 2, 1/2, and tangent, we have opposite, square root of 3 over adjacent, which is 1. So the tangent of 60 degrees is just the square root of 3. If you were to type, for example, the sine of 60 in your calculator, remember we need to be in degree mode, you're going to get an irrational number. It is equivalent to if you were to take the square root of 3 divided by 2. So you'll see that you'll get the same decimal on either side because they are equivalent to one another. But this is an exact value. All those numbers your calculator spits out, those aren't exact. Let's take a look at some examples here. So in the first question, we're asked first of all to sketch each angle in standard position and state the quadrant in which the terminal arm lies. So I know if it's in standard position, I need that vertex on the origin and I need one of those rays on the positive x-axis. And from there, we're going to rotate that ray 150 degrees and we're going counterclockwise. So we're going to go 90 degrees and then we're going to keep going and 150 would be about there. If we were to keep going, this is 180. So we're not quite going to get to 180. We're going from here, 90, and then over to 150. This next one, we're rotating 240. The vertex is at the origin. The one ray is at the positive x-axis, and now we're rotating. So we're going 90, 180, 240. We're not quite down at 270, which is what that negative y-axis would be. So we are terminating in quadrant 3. Now, in terms of the reference angle, remember the reference angle is between the x-axis and the terminal arm. So in this first one, this here is my reference angle. And then over here, between the x-axis and my terminal arm. So then I know that right here, this is going to be my reference angle. So we can visually see that if this is 180 degrees, take off 150, that reference angle would be 30 degrees. And then over on this one, I know that if this is 180, I'm going another how many degrees to get to 240. So we can take our angle of rotation, take off the 180 degrees here, and that leaves us with our reference angle of 60 degrees. In this next question, we have a metronome, and I put a picture here just in case you're not familiar with it. It's a device that musicians use to keep track of their beat. So this arm will swing back and forth at regular intervals, making a tick noise each time. So this is the pendulum arm, and it's 10 centimeters long in this particular metronome. It is swinging from 45 degrees to 135 degrees, and we are looking for the exact horizontal distance that tip of the arm is going to travel. So I kind of sketched it out here. So let's say it's going from 45 degrees, that's where it starts, and then it's swinging over to 135 degrees. Now we're looking for the horizontal distance it's going to travel. This is 135 degrees. I know that this angle in here is going to be 45 degrees, and we're looking for this horizontal distance here. So you might recognize right off the bat, if this is 45 degrees, because this makes a 90-degree angle, I know this also has to be 45 degrees. We know that the arm length is 10 centimeters, and I know these two sides are the same because we have an isosceles triangle. So you might even say, okay, if this is x, this also has to be x, and this hypotenuse is 10 centimeters long. So we can even just set up Pythagoras' theorem. X squared plus x squared is 2x squared. And then we can divide out that 2. 100 divided by 2 is 50. Square root to get rid of that squared. And then we can always pull a perfect square of 25 out of there. The square root of 25 is 5, and we're left with a 2 in the radicand. That's going to give us x. Double that, and we will get the horizontal distance. Now, if this was not an isosceles triangle that was formed, we can also go about this another way and say that we do have a special triangle here. So I know it's an isosceles triangle, and again, if this is 45 degrees, I know this is also 45 degrees. So this is the relationship we have in that special isosceles triangle. In our particular triangle, I'm looking for that x. I know this is 10 centimeters. Now, we know from our special triangle, if we have a 45-degree angle, I want to use this root 2, so we can choose either the sine or the cosine ratio. So let's maybe go with sine. So from this angle, sine is going to be opposite over hypotenuse, rationalize, and we're going to get that square root of 2 over 2. So in our case, we're looking for x. We know the hypotenuse is 10. Therefore, this square root of 2 over 2, that's going to be, again, from that 45-degree angle, equal to r opposite over r hypotenuse. We now have a proportion that we can go ahead and solve. So we're going to go 10 times the square root of 2 is 10 root 2, divided by 2 is going to give us that same 5 times the square root of 2. That's the value of x. We're looking for that horizontal distance, so we need to double that. We're going to multiply that by 2, and we know that the exact horizontal distance we're traveling is 10 times the square root of 2, and again, make sure you put some units on there. And then in our last example here, we're taking an angle of 60 degrees and we are reflecting it, first of all, in the y-axis. So my original angle is drawn in blue here. This y-axis becomes my reflection line, so if we reflect over, I have a reference angle of 60 degrees. I'm looking for that angle in standard position. So I know if this is 60 degrees here, I've got 180 minus 60, I have a 120 degree angle from here to here. If I reflect in the x-axis, so here's my original 60 degrees, now we reflect this way, so I again have a reference angle of 60 degrees. My angle in standard position, we're looking, what's the measure from here all the way around to here? So I am 60 degrees shy of a full 360 degree circle. So I know that this angle is going to be 300 degrees, and then in the last one, we start with that 60 degree angle. We reflect first of all in the y-axis, so this is 60, then we reflect down to the x-axis, so this is also 60. So in this one, you can see we're going 180 degrees plus another 60. I know this angle of rotation is 240 degrees.